Hi everyone, Assalamualaikum. In this video, we are going to continue with properties of limits. There are 7 properties of limits. Okay, now we look at one by one. The first one, we have constant rule. Okay, if we have limit x approaches a, c, where c is a constant, it is equals to constant c, because there is no variable x to substitute here, right? Properties number 2 is constant multiple rule. Limit x approaches a, c, which is constant fx, will equals to c, limit x to a fx. Okay, we can move out constant c from limit expression. That's why we get this, right? We can move out constant only and never move out variable from limit expression, right? Properties number 3, addition and subtraction rule. Right, limit x to a fx plus gx will equals to limit x to a fx plus limit x to a gx. Okay, we separate the limit. Okay, and if we have limit x approaches a fx minus gx, it will equals to limit x approaches a fx minus limit x approaches gx. Okay, when we have addition and subtraction, we can separate the limit. Alright. Properties number 4 is multiplication rule. Okay, if we have limit x approaches a fx times gx, we can write limit x to a fx times limit x to a gx. Okay, we separate the multiplication of limits. Alright. Properties number 5 is division rule. Okay, limit x approaches fx over gx is equals to, we separate the division, so we get limit x to a fx over limit x to a gx. Okay, and limit x to a gx not equals to 0. Alright, now we continue with rule number 6 or properties number 6, which is power rule. Limit x to a fx to the power of n will equals to limit x to a fx to the power of n. Means that the limit for fx to the power of n will equals to limit fx to the power of n. Alright? And properties number 7 is root rule. Okay? If we have limit x to a and root of fx, we can write and root of limit x approaches a fx. Okay? Means that limit for the function for n root of function will equals to n root of limit x approaches to a fx. Alright? And n here must positive integer. Right? Evaluating the limits. There are several ways to evaluate the limits. Number 1, evaluating limits using direct substitution. Number 2, evaluating limits using factoring and cancelling. Number 3, evaluating limits using multiplying by the conjugate. And number 4, evaluating limits using squeezing theorem. Right? Now, we look at one by one the examples using the 7 properties of limits. Alright, number 1, evaluating limits using direct substitution. Alright, from Theorem number 1, constant rule. If we have limit x to a, c, where c is a constant, the answer equals to constant, right? We look at the examples. A. If we have limit x approaches 1, negative 2, it is equals to negative 2 using this theorem, right? B. If we have limit x approaches 0, surd 3, it is equals to surd 3, right? Because there is no variable x to substitute here. Okay, and C, if we have limit x approaches negative 2 pi, it is equals to pi. Pi means constant because pi equals to 3.14 something, right? So when we evaluate limit for constant, it is equals to constant, right? The limits of constant is the constant because there is no variable x to substitute, right? Got it? Now we look at the example for theorem number 2 for limits, okay? Constant multiple rule. If we have limit x approaches a, c fx, where c is a constant, so we can move out constant c from limit expression. So we get c limit x approaches a fx, right? Right, for example, if we have limit x approaches 1 to x cubed using direct substitution, after we plug in the value of 1 into variable x here, so we get 2 times 1 cubed. Okay, and after we use direct substitution, no more limit expression. That's the way how we solve limit, right? Then we simplify, so we get 2 times 1 cubed is equals to 2, right? Or we can use this theorem, okay? For the same example, okay, when we have limit x approaches 1 to x cubed, using this theorem, we can move out constant c from limit expression, okay? So, we can move constant 2 from limit expression, okay? We move out, okay? So, from theorem of limit, we bring out constant from limit expression, right? Then we have limit 2 times limit x approaches 1 x cubed, right? After that, we use direct substitution. So we get 2 times, we plug in 1 into x here. Okay, so we get 1 and then cube. Okay, so now we have we have 2 times 1 cube and it is equals to 2. Okay, remember, after we use direct substitution, no more limit expression. Alright? So the final answer equals to 2. Okay? So we can use this method or this method. Alright? Now we continue with the examples under theorem number 3. Okay? Addition and subtraction rule. If we have limit x approaches a fx plus or minus dx, we can separate the limits. So we get limit x approaches a fx plus or minus limit x approaches a dx. Okay? From here, we separating the limits if we have addition and subtraction in between here. Right? Right, for example, if we have limit x approaches to x cubed minus 3x plus 1. Okay, now in between is minus and plus. Okay, Alright, if we use direct substitution, we can replace 2 into whatever x here. So we get 2 cubed minus 3 times 2 plus 1. Okay? And remember, after direct substitution, no more limit expression. That's the way how we calculate limit. Right? After that, we simplify, so we get 2 cubed equals to 8. Minus 3 times 2 equals to 6, and then plus 1. So, we get equals to 3. Alright? Or, from the same example, we can use this theorem. Okay? Using this theorem, we separating the limits if in between is plus or minus sign. Okay? So after we separate, so we get limit x approaches to x cubed, and then minus limit x approaches to 3x plus limit x approaches 1. Alright? And after that, we substitute 2 into whatever x here. So we get 2 cubed. Okay? And then minus 3 times 2. And then plus 1. Okay? Remember, after we use direct substitution, then no more limit expression. Okay? When we solve limit x approaches to 1, this is actually under theorem number 1. Okay? Where when we solve limits for constant, it is equals to constant. Okay? Alright, for limit x to 3x here, it is actually under constant multiple rule. We can move out constant 3 from limit expression. Okay, or we can straight away use direct substitution like this, right? So after we substitute 2 into whatever x, we get this. Okay, and remember, after we use direct substitution, no more limit expression. Right? Then we simplify, so we get 8 minus 6 plus 1, and then equals to 3. We get the same answer. Alright? So you can use this method or this method. Okay? Look at example 4 under application rule. If we have limit x approaches a fx times gx, we can write limit x to a fx times limit x to a gx. We're separating the limits when we have multiplication of function. Okay? Right, from limit x approaches negative 1, x squared times x minus 1. Okay? If we use direct substitution, we're plugging negative 1 into whatever x here. So we get negative 1 squared times negative 1 minus 1. Okay? And remember, after direct substitution, no more limit expression. Okay, that's the way how we calculate the limits. Right? Then we simplify, so we get negative 1 squared equals to positive 1. Negative 1 minus 1 equals to negative 2. And 1 times negative 2 equals to negative 2. Right? Or, for the same example, we can use theorem of limit. We're separating the limits. Okay? So we can write limit x approaches negative 1 x squared, and then times, we're separating the limits, limit x approaches negative 1 x minus 1. Okay? From here, we use direct substitution to evaluate the limits. Okay? So we have negative 1 squared we substitute negative 1 into whatever x here. So we get negative 1 squared times, we substitute negative 1 into x here. So we get negative 1 minus 1. Okay? And remember, after direct substitution, no more limit expression. Alright? After that, we simplify. So we have negative 1 squared equals to positive 1. Minus 1 equals to minus 2. And 1 times negative 2 equals to negative 2. Alright? You can use this method or this method. Okay? You will get the same answer. Alright? Example 5 under division rule. Okay, if we have limit x approaches a fx over gx, it is equals to limit x to a fx over limit x to a gx, and limit x to a gx not equals to 0. Right. For example 5 here, we have limit x approaches 0, x minus 1 over x plus 1. Okay, this is a division function. Okay, when we use direct substitution, we just replace 0 into variable x here. So we get 0 minus 1 over 0 plus 1. Okay, after we use direct substitution, no more limit expression. Alright, then we simplify. So we get negative 1 over 1 and equals to negative 1. Right? Or for the same example, limit x to 0, x minus 1 over x plus 1, we can use the properties of limit here. Okay? Separating the division of limits. Okay? So we can write limit x approaches 0, x minus 1 over limit x approaches 0, x plus 1. Okay? And after that, we use direct substitution. So we replace 0 into whatever x here. So we get 0 minus 1 over 0 plus 1. Okay? And remember, after we use direct substitution, no more limit expression. Okay? That's the way how we calculate the limits. Alright? And after that, we simplify. So we get negative 1 over 1. And equals to negative 1. We get the same answer. So you can use this method or this method if limit x to a gx not equals to 0. Right? We continue with example 6 under power rule. If we have limit x approaches a fx to the power of n, we can write limit x to a fx bracket to the power of n. Right? We can move out the power of n from limit expression. Right? Right now we look at limit x approaches to x cubed. Okay? So if we use direct substitution, we just replace 2 into variable x here. So we get 2 cubed. Okay? And after we use direct substitution, no more limit expression. Okay? Then we simplify. So we get 2 cubed equals to 8. Alright? Or, from the same example here, limit x approaches to x cubed, we can use this theorem. Okay? The limit of cube of a function is equal to the cube of the limit of a function. Okay? So we can move out cube from limit expression here. So we get limit x approaches to x bracket to the power of 3 or cube. Okay? And after that, we plug in 2 into variable x here. So we get 2 cube. Okay? And after we use direct substitution, no more limit expression. Alright? After that, we simplify, so we get 2 cubed equals to 8. Okay, we get the same answer. So you can use either this method or this method. Okay, in this method, we use theorem. Okay, we use power rule. Right? Right, now we look at example 7 under root rule. Okay, this is the last rule under properties of limits. Okay, if we have limit x approaches a and root of fx, it is equals to and root of limit x approaches a fx. Okay, we can move out and root from limit expression. Right? For example, if we have limit x approaches to cubic root of 4x, if we use direct substitution, so we can replace 2 into variable x here. So we get cubic root of 4 and then times 2. Okay? And remember, after we use direct substitution, then no more limit expression. Alright? And then we simplify inside cube root here. So we get 8. Okay, 4 times 2 equals to 8. So we get cube root of 8. And it's equals to 2. Right? Or from the same example, when we have limit x approaches to cubic root of 4x, using this theorem, the limit of cube root of a function equals to the cube root of the limit of a function. Okay, so we can write this. We move out cubic root from limit expression. Okay, so we get cubic root of limit x approaches to fx. Okay, after that we use direct substitution. So we just replace 2 into variable x here. So we get cubic root of 4 and then times 2. And remember, when we use direct substitution, no more limit expression. Alright? Then we have cubic root of 4 times 2, which is equals to cubic root of 8 and equals to 2. Alright? We get the same answer. Okay? You can use this method or this method. This method, we use theorem. Okay? We move out cube root from limit expression. Alright? Important facts about limits. Functions with direct substitution property are called continuous at a. As long as the answer gives a real number, we can use direct substitution to evaluate limits. However, not all limits can be evaluated by direct substitution. The next video are some other techniques that can be used. Right? Coming up next, method 2 to evaluate limits, which is evaluating limits using factoring and cancelling. If you like this video, you can subscribe. Thank you for watching. Stay tuned. Bye. Assalamualaikum.